I've just had a little disaster, which is that I've made my longest ever recording of a video of myself solving some problems, or so I thought. It lasted about an hour and a half, and I got to the end, and it seems that I'd not recorded myself. I'd just been talking, thinking I was recording myself. And so I think the best I can do under the circumstances is just to talk very, very quickly through what I actually did for the problems. I've got what I wrote. And in some ways it's good, because what actually happened was that there were a few problems that were boring and easy. And then one problem that I had in fact seen before but not solved, and was not so easy at all, and it took me a long, long time, and I haven't completely solved it, but I think I've broken the back of it. So I will just, in some ways, in fact, I think this may be a good thing, because the video itself would have been a lot of me just playing around, trying things out over and over again. And I think if I just make a much shorter video talking about what I did and how I eventually came up with what I came up with, that may be actually a bit, from a point of view of watching, a bit more interesting. So let me just get up what I wrote. It was very disappointing when I first spotted what I'd done. So the first question was, does the sequence of squares contain an infinite arithmetic subsequence? And the answer was just obviously no, because basically the squares, the distances between successive squares, get bigger and bigger. An arithmetic subsequence I'd take to mean an arithmetic progression. So an arithmetic progression, if it's got common difference d, then if you go far enough in the squares, there just aren't any two squares that differ by d, so because all their differences are bigger than d. So I couldn't understand why that question was asked, really, and in what sense it's to do with invariance. Next one, the integers 1 to n are arranged in any order. In one step, you may switch any two neighbouring integers. So this was just, prove that you can never reach the initial order after an odd number of steps. So I decided not really to do that in much detail, just because it's simply saying that the identity permutation is not an odd permutation. So if you know about even and odd permutations, then it's just trivial that this is the case. And so the question boils down to, I suppose it was aimed at people who had not heard of even and odd permutations, and they needed to discover the invariant, namely the parity of the permutation. And I just remarked that when I was at school, one way of the way I was taught what the parity was of a permutation was that if you write out the numbers and then you write out their images, it's the number of crossings. And of course you have to prove that that's an invariant, and check also that if you do a transposition, you can do it first with neighbouring elements. 37 was prove the same thing, except you can switch any two integers, not necessarily neighbouring ones. And again, if you know about even and odd permutations, that doesn't make too much difference. So it didn't seem worth dwelling on those. And then the next question was, you're allowed to do a transposition pair. You're allowed to take 4 numbers and switch 2 of them and switch the other 2 of them. And the question was, can you reverse, if you start with the integers from 1 to n, can you reverse the order so it goes down from n to 1 by doing a succession of these switches? And the question was, prove that it depends on the parity of this number here. And the way I did it was simply to observe that that's an even permutation, so we just have to work out the sign of the permutation that switches the numbers from 1 to n. And that was not terribly interesting. If n is odd, you can check that it works out to be a parity of n minus 1 over 2. And if n is even, it's a parity of n over 2. And in both cases, those are equal to the parity of n minus 1 over 2. And then I remarked afterwards, probably I could have just also thought about the parity of the permutation that switches being n minus 1, because you have to move that one right to the end, and then you have to move that one past n over 2 things, that one past n over 3 things, and so on. So you get the sum of the numbers from 1 to n minus 1, which is this, again, this number here. So still not a totally interesting question. And then suddenly, bang, we had a very interesting question. So, and this was a question, as I said, that I had seen before, but I hadn't solved it, and I'd not, as I said again, well, I'd not worked on it to the point where I really was going to sort of say, unless I spend hours and hours on this, I'm not going to give up. I think I've tried it a bit and didn't manage to solve it, and then didn't come back to it. I didn't get to the point where I was determined to solve it. So I was a bit scared of this question. So what happens? You have a bunch of chips which can be put onto coordinates, non-negative integer coordinates, which actually the question thinks of as squares. So the question says label each square by the coordinate of its lower left corner, but it's not too important. You could also imagine putting chips actually onto the points themselves. It makes no difference for this question. And you start off by putting a chip on each of, I'll draw this in. So the starting configuration for A is you put it on the sort of first 6 squares. That's 0, 0, 1, 0, 2, 0, 0, 1, 1, 1, 0, 2. And in any move, what you're allowed to do is remove one chip, like this one, say, and as long as the 2 neighboring places are free, you can replace it by a chip on the 2 neighboring places. So it's got to be above and to the right. So here now I can't replace this one because that one's in the way. But if I wanted to replace this one, I could get, first of all, replace that one by 2 like that, and then replace this one by 2 like that. So that would, and I used a cross to designate a sort of unoccupied point in the grid. And so this one's now stuck, that one's not stuck, that one is stuck, and so on and so forth. So that just gives an idea of what moves in this game, so to speak, look like. And actually it's coming back to me where I saw this problem. I think I saw it during the first lockdown. I think Mike Lawler may have mentioned it. But if you don't know who Mike Lawler is, I recommend Googling him because he has a lot of interesting content online, including videos. So what you see here was an attempt. So the question was, 1, can you escape if you've got one in those 6 squares? What about if you just got one in the very bottom left-hand corner? Can you then make sure that there are no chips left in any of those 6 squares? Or 6 points. And the slightly scary aspect of this question was that it was posed by Maxim Kontsevich, who is one of the most famous mathematicians in the world, with very good reason, and has proved some extraordinarily difficult theorems. And so I don't know what TT stands for, but I'm guessing it's some sort of maths competition. And I worked out that Kontsevich must have been in his late teens then. I know that because I happen to know he's roughly the same age as me, and I was in my late teens in 1981. All right. So this was just the point at which I gave up after attempting to escape with, I can't remember now whether this was an attempt to escape with just 1 point to start with, or whether I had 6 points to start with. When I began this, I had this strange idea that maybe if you started with 6, it would actually be paradoxically easier to get them all to escape than if you started with 1. I think I was thinking of things like solitaire, to get the version of solitaire where you have things that hop over other things, and sometimes having extra pieces around can make it easier to get rid of things in the end. Bit later on, I realized that actually there was a simple monotonicity argument. The more chips you've got, the harder it is to get them to escape. It's sort of almost trivial, because if you just remove a chip, it creates empty spaces that you didn't have before. So once I realized that the possibilities for this question are, it's always possible. I mean, possible for both things, or it's impossible for both, or it's impossible in the first case and possible in the second case. Those were the possibilities that seemed reasonable. And so the reason that I spent a long time on this problem was that I just tried an awful lot of things. I produced quite a nice lemma at some point. Perhaps I'll just quickly go down and explain what that lemma was. It was that if I ever have two things like that, then I can, with nothing above them, then I can replace the first one by, so I've got the second one down here, by this, and I can replace this by this, and then I can, I've left a space for this one, so I can replace that by that. And so the two that used to be there have become a bunch of three followed by another two. And what's somewhat nice about that is that you can iterate it. And so you get another 3 plus another 2, but then you can sort of iterate over and over again and just create an arrangement where you have things going up and up like that. So for example, if I start with 1 square, then I can get 2 things here, and then I can convert it into this. So if I start with 1 square, then a question becomes, can I get these 3 all to escape, if this is my configuration? And I couldn't see how to do it, and in fact I came up with an argument that convinced me that it could not be done. And the argument was roughly that if I move this one, so I fill those squares, and this one's in trouble, so I've got to get rid of this. But in order to get rid of this, I've got to move both of these. So in order to move both of these, I have to move both of these. But in order to move both of these, I therefore have to move both of these. But in order to move both of these, and so on. And supposing I've only gone finitely far with this, I'm still sort of a bit in trouble, because I can't even move either of those, so I will actually have to move this out of the way, and then I've still got to move both of those. So we could say that at some point I've got to get rid of this. But also at some point I've got to get rid of this, so at some point I've got to get rid of this. Slightly hazy about whether the order in which I do it matters, so I've got to get rid of this. And I've just moved the problem up by 1. So I think I convinced myself sort of up to a point that this was a position from which it was not possible to finish off. What else happened? So you see that things start. So at some point, as I say, it occurred to me that it was going to be harder to do it from the 6. So I then started thinking, right, after a lot of playing around, I thought, now let's think about invariants. Let's try and think what sort of invariant could possibly stop it being possible to escape from those 6 squares. And at first I started thinking, well, what about, there be something that doesn't change when you move when you replace a square here or a chip here by two chips just next to it, then I made the observation that if you started with the arrangement, so this was what this diagram was a relic of, so if you started with this arrangement, so you've got one point in here, then of course you can escape from that very easily. You just do a single move, and now we've escaped from those 6 squares. So there's not going to be an invariant that doesn't change whenever you do a move and distinguishes between arrangements where there is something in these 6 squares and arrangements where there's not something in these 6 squares. But there might be something that distinguishes between the starting arrangements and arrangements where there's nothing in those 6 squares. And then I started thinking, well, it's just what do we know? There's definitely something that's helping to make things difficult, and that is just the number of chips there are around. So after you've done n goes, you've got you started with 1 chip, so I suppose after you had n turns, you've got n plus 1 chips, and those are clogging things up. But they're not clogging things up so much if they're far away. They're only clogging things up if they're close by. So that got me thinking about the distance that you are away. Where was that? Yes, so I wrote down the number of chips goes by 1 each time. I wondered about the sum of the distances from the origin, but that was a bit difficult to think about because say I've got a chip at distance d, then so I was measuring distance, by the way, by the number of steps that you take if you go to the right or up from the origin. So the initial thing, you've got 1 chip at distance 0, or you've got 6 chips, 1 at distance 0, 2 at distance 1, 3 at distance 2. So if I just look at the sum of the distances, then when I go from 1 that's at distance d, I'll have 2 that are at distance d plus 1. So the sum goes up by d plus 2, because it went up from d to 2d plus 2. So the amount by which the sum goes up depends itself on the distance, and that wasn't very nice. So actually I replaced it by something else that had that property, but I thought, what about if I attach, so if I've got some number associated with this point here. I somehow wanted the idea that when I replace it by 2 chips, their distance has gone up by 1, but if I didn't take the average of those 2 instead of the sum, then I've got something that goes up by 1. And actually that turned out, I couldn't quite make sense of that so that it was a true statement. But nevertheless, it turned out to be quite a useful idea that I start with a chip at distance 0. And then I replace that by sort of half a chip at distance 1 and another half a chip at distance 1. Then here I've got a quarter of a chip at distance 2, quarter of a chip at distance 2, and so on. Now what happens when I move a chip from distance 0 to 2 sort of half chips at distance 1? Then I go from the sum of the distances being 0 to the sum of the distances being sort of half a chip at 1 and half a chip at 1, which makes 1. So it goes up by 1. If I make this half and split it into a quarter and a quarter at distance 2, it went from a half times 1 to a half times 2, so it's added a half. So each time I move a chip from from diagonal number d, the diagonal distance d to the diagonal distance d plus 1, I'm making an extra 2 to the minus d, to the total of what? Well, when you think about it, I'm looking at the sum of all the distances of d over 2 to the d. So it starts off with, and so here was sort of thinking about what might happen. We might start with a 0. On the first go we get a half 1 plus a half of 1. On the second go, if we split that into 2, we get a quarter times 2 plus a quarter times 2, still have this half 1. Then I was initially thinking, well, let's just scrap the rule that you can't have more than one chip on the same square. So that would enable you to, as I say, well, put two things on the same square, and you could have a quarter two plus a quarter two plus a quarter two plus a quarter two. But I stopped thinking about that after a bit. So here's just another move. I've taken that and replaced that thing at distance 2. I've replaced it by two things at distance 3, which then get an 8th in front of them. And this is what was going on with the sum of d over 2 to the d as I did that. And then I made the observation that if we start with the 6 chips in these positions, then what do we get? We get 0 plus a half plus a half plus a quarter plus a quarter plus a quarter. So that's 1 3/4. Is that really what I mean? No, it's not. So it's 0 plus a half plus a half plus 2/4 plus 2/4 plus 2/4, which is 5/4 for the starting configuration. Let me just quickly check that I really mean that. So it should be what I've written here. So 1 plus 6 over 4, which is 3 over 2. So 5 over 2 I should be getting. Why have I written 3 times 2 over 4? Two to the d when the distance is 2 is 4. So I'm dividing by 4, and I have 3 of them. I seem to get 7 over 4. So why did I say 3 times 2 over 4? Perhaps I shouldn't have. I think I wrote down something nonsensical, so that gives me something to do. So let's explore this invariant that I came up with, sort of half by accident, half by thought. So my invariant is sum over all chips of the distance from the origin divided by 2 to that distance. And so if my starting configuration is this, so I had something more complicated that I think was wrong. If I start with this, then what is the initial value? It's 1 times 0 over 2 to the 0 plus 2 times 1 over 2 to the 1 plus 3 times 2 over 2 to the 2. Oh, so it was right in that case. So that's 0 plus 2 over 2 plus 3 times 2 over 4. Is that what I wrote? Where's it gone? Yes, it is. So sorry, I went wrong just now for some reason. We'll just check what the next one would be if there were 4 things here. It would be 4 things. They're all at distance 3, and then I have to divide by 2 to the 3. 4 times 3 over 8. Hope that's what I wrote. Yes, it is. Okay, so back to what I was saying. That's the value of the invariant. But if everything ends up outside the 6 squares, then the value that the invariant is going to be is at most all the sum of this thing over the remaining squares, which is this thing here. So I did a sort of back of envelope calculation and convinced myself that this sum here is going to be at most 6. In fact, less than 6. I didn't check that super carefully, but I was fairly sure it's going to be less than 6. Whereas, and it goes up each time, because each time you replace a chip by 2 things, it goes up by 2 to the minus the distance that you went up from. So unfortunately, this number here is 5 over 2, whereas this number here is, if that number is less than 6, but 5 over 2 is a lot less than 6 already. But working in our favour is the fact that to get all those chips out, we're going to have to do quite a lot of adding to the value of the invariant. So it's not just that we've started with a certain value, we're going to have to add quite a bit to it. And that's basically how I finished things off. So I reasoned that we started with 5 over 2. Our target is to prove that we're going to have to end up being greater than 6 at some point after we've done these moves. And so each of these 3 things, they're at distance 2. So they make a contribution of 2 over 2 to the 2. And so when you go from 2 over 2 to the 2 to twice 3 over 2 to the 4, the 2 over 2 to the 4 is a 2 over 2 to the 2. So you go from so let's write that as 4 over 2 to the 3. Well, let's just do it explicitly. 2 over 2 to the 2 is a half. Thought this one was going to be a... So why did I say 2 over 2 to the 2? So this chip contributes to the sum an amount, the distance, it does, it contributes 2 over 2 to the 2. And afterwards, when you've moved it, it will contribute 3 over 2 to the 3. 2 over 2 to the 2 is not just once though, but twice. So it goes from a half to 3/4, so it adds a quarter, but it does that. Yeah, it adds a quarter. So from this chip, we get a plus a quarter. That happens for each of those 3. So we certainly get to add at least 3/4 to the total. What about this one? It's going to add, it starts off at 1 over 2, and then there are going to be at least 4 things now that have distance 3. Divided by 8. So that's this one. By the time it escapes, it's got to have reproduced into 4 chips, each of which will have distance at least 3/8. So 4 over 8 is 1 over 2, that's 3 over 2. So this thing has added at least 1, and this one's added at least 1, so plus 1 plus 1. And this one here goes to, first of all, a half. Oh, sorry, I think I might have just. Oh, so that was okay. So this naught, one at distance naught, was originally contributing naught, and it, by the time it escapes, 1, 2, 3 steps. It's going to have to. There'll be at least 8 chips somewhere out here. So it'll go up to 8 times 3 over 2 to the 3 from naught. So it goes up to 3. So I'm going to add a 3 or something like that. So the total increase in the invariant is something that looks like a number that is really a lot bigger than 6. And so that's my proof. Not quite checked to full standard I'd like, but anyway, that's my proof that we can't get all these 6 out. And I think, but now I'm much less sure of myself about this, but I think that if you start with just 1 and a bit more careful, so you argue, so the first thing you do is going to be this, which will have already added 1. If you start, so this argument here just allowed everything to accumulate on the 4th diagonal, and I didn't mind if chips were on top of each other and all sorts of things like that. But this, I think if you're a bit more careful and analyze sort of what else can't happen, I think it will be possible to argue that the invariant is eventually going to have to climb above 6. Certainly there's a sort of finite check you can do. So when I said I've broken the back of the problem, that's because I've not proved that you can't get a single chip in the origin out, and I think it's conceivable that you can. But if you can't, I've got a fairly good... I'm fairly convinced that you can't, actually, after trying it a few times and doing fairly natural things and getting into trouble. So that was really where it all ended up. I have pretty much a proof that you can't do it for this, and a plan for a proof, not really executed, but a plan for a proof that you can't do it like this. Because it's only a plan for a proof, it's possible that I'm wrong and that you can. And there were some methods of potentially doing it that I didn't fully explore. So this was a slightly strange video, and it wasn't really me solving things in real time, but it was me reporting very soon after having had the thoughts what happened. So that's the best I could do under the circumstances given my accidental non-recording. Let's hope I've recorded this time. There seems to be a red thing that's going on and off, so I think I have. So I'll stop there. But you may enjoy just seeing whether you believe me that you can't get this one to escape.